Good morning, everyone. This is Lokesh Chaudhary from Aeronautical Branch. Roll number 2495182122. Today the subject is data structures. Today the subject is about data structures, and the course code of this subject is ACS D08. ACS D08. The topic in the data structures today we are going to discuss is about modularity defines new ways of processing. Introduction to community aware graph signal processing. This graph signal processing is known as GSP. So the graph signal processing GSP extends the classical signal processing to data defined on irregular structures like graphs. Community aware GSP incorporates community structures within graph to enhance processing techniques. This presentation explores how modularity influences new methods for processing graph signals effectively. GSP is known as a graph signal processing. Basics of graph signal processing. GSP graph signal processing involves analyzing signals that are indexed by graph nodes, capturing complex relationships. Traditional GSP graph signal processing methods often assume uniform signal behavior across the graph. Incorporating community structures enables more nuanced and context-aware signal analysis. Understanding graph communities and modularity. Communities group nodes with dense internal connections and spans external links. Modularity is a measure that quantifies strength community structures within a graph. High modularity indicates well-defined communities which are crucial for community-aware processing. Significance of modularity in graph analysis. Modularity driven approaches can reveal hidden patterns not apparent through tradition methods. Limitations of traditional graph signal processing. Conventional methods often overlook the underlying community structure of graphs. Ignoring communities can lead to suboptimal filtering and outcomes. There is a need for techniques that explicitly incorporate modularity into a processing pipeline. Community aware signal processing framework. A framework that considers community structures, enhances the interpretability of signals. It involves defining the community modularity. This approach allows for localized processing that respects community boundaries. Modularity based graph for Fourier transform. Graph Fourier transform graph Fourier transform is a GFT graph Fourier transform reflecting community structures. This transforms signals in a way that emphasizes community related features. Community driven filtering techniques. Filtering can be tailored to reinforce or suppress signals within specific communities. Modularity based filters improve denoising by preserving community specific information. These techniques offer more precise control over the manipulation of graph signals, enhancing signal denoising with modularity. Denoising benefits from understanding community boundaries to prevent signal distortion. Community-aware methods adapt filtering parameters based on community strength. Results demonstrate improved signal fidelity compared to traditional methods. Community-aware signal clusters. Clustering leverages community structures to group similar signals. Modularity guided clustering enhances the declaration of signal patterns. This approach is useful in applications like anomaly detection and segmentation. Applications in social networks. Community-aware GSP analyzes user behavior within social groups. Modularity helps identifying influential communities and their signal dynamics. Applications include targeted marketing and misinformation spread analysis. Applications in sensor networks. Sensor data often exhibits community structures based on physical proximity. Modularity informed processing improves anomaly detection and environmental monitoring. Community-aware techniques enable localized and efficient data analysis. Data analysis. Applications in brain connectivity analysis. Brain regions form functional communities with distinct signal patterns. Modularity-based GSP offers insights into neural activity and disease states. This approach supports more accurate brain network modeling and diagnostics. Benefits of modularity-driven processing. Incorporating community information leads to more accurate and meaningful analysis. It enhances interpretability by aligning with natural groupings in data. Modular approaches are adaptable to various graph-based signal processing tasks. Challenges in community-aware GSP. GSP is the process identifying optimal community partitions remains computationally challenging, balancing community detection accuracy with processing efficiency. Okay. Future directions in community-aware GSP. Developing scalable algorithms for large-scale community, exploring adaptive methods that dynamically update community structures. Extending modularity-based techniques to multi-layer and temporal graphs. Summary of the key points. Modularity is a powerful measure for understanding community structures in graphs. This is Lokesh signing off. Thank you.